Okay, good morning. And sorry for a little delay. So we were looking at classical cryptography. I have talked about a couple of crypto systems, classical crypto systems. Then we talked about cryptanalysis, how to break them. And so that means then we answer that question when we can say that the crypto system is perfectly secure. That means even if we are given a encrypted text, we will not be able to find the plain text, right? So this is Shannon criteria. So basically the Shannon definition in terms of probabilities. So we talked about a couple of concepts from elementary probability theory, like discrete random variable, right? So we have a finite set and a probability distribution on X, which is a discrete random variable. Then we have joint probability, conditional probability, independent random variable. This theorem is quite useful, and people who are in data science, they will also love this theorem, right? Then perfect secrecy. I talked about so a crypto system consisting of plain text space, ciphertext space, key space, encryption rule, decryption rule is perfectly secure if this happens. If conditional probability of X condition Y is same thing as probability of X for every X in plain text and every Y in ciphertext, right? So you know that so each plain text, ciphertext, and key can be looked at as a random variables, right? So this is the key idea, and then you check this condition. And I have shown you about this result, which uses Bayes theorem and other some calculations to show that that if 26 keys in the shift cipher are used with equal probability 1/26, then for any plain text probability distribution, the shift cipher has perfect secrecy, right? So this is the result that we obtained by applying these calculations, probabilistic calculations. Now, there is a characterization of perfect secrecy, which one can actually normally uses. So, I'm going to talk about that. And before talking about that characterization of perfect secrecy of Shannon, I need to build few more concepts, and then we talk about this characterization. After that, you will see that another very important concept you might have heard is entropy, right? So nothing is, you cannot talk about digital communication without entropy and other things. It's a very, very fundamental concept. Though entropy was originated in thermodynamics, in physics, and now how Shannon used a similar idea, and they talked about entropy of a random variable, right? And then I'm going to talk about, probably you have done already these things again, so just really brush up. So we can talk about probability of random variables. So now since we have plain text as a random variable, ciphertext as a random variable, and key as a random variable, so I can talk about entropy of these things, and you will see that how this idea of entropy is really useful in understanding the crypto system. Okay. Okay. So now some of the building things, right? If probability of x naught is equal to 0 for some x naught in the plain text, then obviously this condition will be trivially satisfied, right? If probability of x naught is equal to 0 for every y in C, right? So we are going to look at only those plain text x in P such that this probability is positive, right? Now we know that uh, for perfect secrecy, probability of x condition y should be probability of x for every y in C, right? This is equivalent to this probability of y condition x is equal to probability of y for every y in C, right? These two things are equivalent, right? So therefore, we can assume that this probability is positive for every y in ciphertext, right? Now, if once this assumption is there, we can fix any x, a plain text in P for each y in C. We will have, because of this condition, the conditional probability of y y condition x is equal to probability of y, which is positive, right? So we have this simple observation. So that will lead to, now this condition here will lead to that for each y in C, there must be a key such that encryption, so there must be more than one keys k such that encryption of k x is equal to y. That means the size of key space is more than the size of the ciphertext. Okay. Now in cryptanalysis, because of the injective mapping, right, the encoding rule is injective. The size of ciphertext space is more than the size of the plain text space, right? So basically, these are some other observations. Now we have this characterization for perfect secrecy. So this is given by Shannon. So if PCKED is a crypto system, P is the set of plain text, C is the set of ciphertext, K is the key space, encryption rule, decryption rule, and we have this condition that the size of key space is same thing as size of ciphertext is same thing as size of plain text. Okay. So then our crypto system is perfectly secure. It's perfectly secure if and only if every key is used with equal probability 1 over 1 by k, size of k. And for every x in the plain text and every y in the ciphertext, there is a unique key k such that ek of x is equal to y. So this, of course, I will prove one part, but other part you can enjoy at your tea, right? So the converse part. So obviously, I will prove the easy part. So the easy part is that we assume that the system is perfectly secure, and then we can do some calculations to arrive at this result, right? So first of all, we need to say that so there is a unique key. So it is not possible that there are two keys k1, k2 such that ek1 of x is equal to ek2 of x is equal to y, right? So it's a unique key should be there. So let us do. So our assumption now will be, so obviously this condition is very important. The size of key space, same thing is size of ciphertext space, same thing is size of plain text space, right? Even if you don't understand the proof, don't worry. I mean, So what I'm saying that at least you should remember the characterizations. Okay. So whenever you are trying to build a crypto system, you can just check, whether it is perfectly secure or not. So in future, even if you come up with a new crypto system, you should remember. So I think important thing is that you should remember this result. In fact, there are many more things. I'm not going to talk about any. At least this much is enough for you to understand. Okay. Okay. So as I mentioned, suppose we are assuming that the system is perfectly secure. So suppose it provides perfect secrecy. Now for every x in the plain text and every y in the ciphertext, there exists a key such that ek of x is equal to y, right? Now this means size of ciphertext space is set of all such things, encryption of x, right? Is the ciphertext. Ek of x such that k is in k. The size of this will be size of the ciphertext, right? By definition, right? Now this thing will be, because there exists key, right? This thing will be less than or equal to size of the key space. But we know that size of ciphertext space is size of key space. This is our assumption given. This implies that this quantity here, size of ekx such that k belongs to k, is same thing as size of the key space. Now, once we have this, that means there does not exist two distinct keys k1 and k2 such that ek1 of x is same thing as ek2 of x equal to y, right? Because of this result. This implies that our key is unique. This implies that there is a unique key k such that x is in plain text, y is in ciphertext, and ek of x equal to y. Okay. So because of this fact here, that size of ekx such that k is in k is equal to size of the key space, our key is unique. Okay. So this is one part. Now suppose there are n keys, and it's the size of k, right? Suppose there are n keys. So that means, we can assume the plain text is something like xi, where 1 less than equal to I less than equal to n. Now fix a ciphertext y in C. Fix a ciphertext y in C. Now, since there are n keys, so I can say that so there are keys k1, k2, k3, kn, such that encryption of each xi with respect to key ki is y. Y is the ciphertext, right? Now, once we have this, then I can compute this conditional probability of xi with condition y, right? Xi is the plain text. So what we are going to do here, so I just compute using Bayes' theorem. This will be probability of y condition xi times probability of xi divided by probability of y. Now, probability of y condition xi is basically we have this probability of k such that k is equal to ki, that key, right? The key space times probability of xi divided by probability of y. Now, for perfect secrecy, we have this condition. The probability of xi condition y is same thing as probability of xi. This is because of the perfect secrecy definition. I can substitute it here and we'll cancel out. So we are left with that probability of ki, which is probability of k variable is equal to ki, is same thing as probability of y, ciphertext, right? For each I between 1 and n. This implies that all keys are used with equal probability, okay, P out of y. Therefore, number of keys, now, since number of keys is size of k, this implies that probability of k is 1 over size of k for every k in k. And that's what you wanted to prove, right? So basically, if you see, our result was that whenever this condition is there, that the size of key space is same thing as size of ciphertext, is same thing as size of plain text, and a system is perfectly secure if and only if every key is used with equal probability 1 over k. So 1 over size of k. So this is a very, very important result. So if you ensure the choice of key, it will give you a guarantee that the system is perfectly secure. So this is something, a very, very important result. Shannon has done everything marvelous, right? So I think you should remember whenever Shannon discovered the result about capacity, the people used to go in his room and look at his blackboard what he's doing now. So every time he's done great work, right? So people try to steal at that time also, but anyway. So that's all about this. So I think now we can talk about entropy. So by the way, what is entropy? Anyone can from the class, since you know this fact, right? Randomness, kind of measure of randomness. By the way, suppose I give you some examples for your tea time problem, right? Tea time problem. So suppose I take a glass of water. So there is some entropy. I put it on my head. So some change. What change? Right? So think about these kind of questions, right? So basically, there are plenty of interesting books. I am sure you have read that book by Thomas. There are some Mackay also written a nice book. Information theory is a beautiful thing. It tells you, for example, bounds, right? What is possible, what is not possible. On the other hand, there is a sister branch, which is coding theory, which tells you how to construct the algorithms, right, which are optimal in that sense. So now I have to talk about entropy of a discrete random variable x. Okay. So entropy is a mathematical measure of information or uncertainty, right? Beautiful concept, like, by the way. So now it is computed as a function of a probability distribution. So suppose x bar is a discrete random variable, and which takes a finite, which takes values from a finite set x according to a probability distribution. So question we can ask: what is the information gained by the output of an experiment, basically, which has which takes place according to the this specific probability distribution. So entropy of x bar we denote it by h of x bar. Okay, so x bar is a random variable. Now I'll motivate it with some examples. If our discrete random variable is a coin tossing, right? So we know that the probability distribution is head is half and tail is half, right? So entropy of a coin toss is, because if you suppose assume head is 1 and tail is 0, so encoding is single bit, so that means the entropy of a coin toss is 1 bit, right? One can think of entropy of n independent coin tossing, obviously will be n, because string, you can think of a string of length n, because encoding will be by length n bits, right? This is another interesting result. Suppose x bar is a random variable, discrete random variable with 3 possible values, x1, x2, x3, and the corresponding probability is half, 1 by 4, 1 by 4. So if x1 is encoded as 0, x2 is encoded as 1, 0, and x3 is encoded 1, 1, okay, the weighted average, that means the number of bits of x will be how much? X1, the probability is half times number of bits used 1 plus x2, which is probability 1 by 4 times number of bits used 2 cross 2 plus again x3, probability 1 by 4 times 2 is equal to 3 by 2 bits, right? So you can compute this. If random variable is given, you can compute this value, right? So the question is, what happens in general? Suppose probability is 1 over 2 raised to power n. So obviously, bit string of length n is encoding. So then, in this case, this value is obviously log 2 base p, right? So in general, we have this formula. If x bar is a discrete random variable which takes on values from a finite set x, entropy of x is defined as minus summation x belongs to x, probability of x times log 2 base probability of x. So my t time problem here, very important problem for you to think. Why all this minus, log, PA, pre-Rx and so on? Why not plus? Yeah, so basically, I mean, think about why do we define entropy of a discrete random variable in this format? It's a very, very important fundamental question. We may ask in the exam also. I'm giving you exam question paper also, right? So why there is a negative sign? Explain like that, why there is no positive sign? Why there is log 2 base probability of x? Why not it is log 2 base 1 over probability of x? So something like this, interesting question. So what you require? A cup of tea to think, right? So this is the entropy of a random variable, some minus summation x belongs to x. So I mean, if formula is given, by the way, we know that log 2 base y, suppose if y is equal to 0, it is minus infinity, right? So how do you compute? Because this will be undefined. Log 0 is minus infinity, kind of undefined. But since we can take the limit kind of thing, limit y tends to 0, y log 2y is equal to 0, under those assumptions, we can compute this value, okay? So even we allow the 0 value. Okay. So these are some observations. The random entropy of a random variable is non-negative for any random variable x, as 0 if and only probability of x naught is equal to 1 for some x naught in x, and 0 for all x not equal to x naught. Okay, so now we have, what is k bar? Random variable associated with the key space. P bar, random variable associated with the plain text, and C, random variable associated with the ciphertext. So one can compute the entropy of each of these things. So best thing is do some example, which is, so this is our previous example that we have taken. Plain text is a comma b with probability of a is 1 by 4, probability of b is 3 by 4. Plain text. Key is k1, k2, k3. So probability of k1 is half, probability of k2 and probability of k3 is 1 by 4. So remember, k is also a discrete random variable. So we have the probability associated with key space, with the plain text, and with the ciphertext. I have shown you how to compute for ciphertext. And ciphertext, suppose, is 1, 2, 3, 4. This is our encryption method. So encryption of encryption of A with K1 is 1, right? All those things you can read. from the table. So entropy of a P will be what? P is a random variable now, discrete random variable. This will be what? First we compute for A, encryption of A, right? So basically A is, what is the probability of A? So if you go to the formula minus, if you go to this formula, I'm just applying the formula here. Minus summation x belongs to x, probability of x, logs 2 base PR of x. For each x in x. So now there are two things, A and B. So I have to compute for both, right? So this will be minus 1 by 4, log 2 base 1 by 4 for A, and minus 3 by 4, log 2 base 3 by 4 for B. So just substitute the values, and this turns out to be 0.81. So now for K and C, the values are 1.5 and 1.85. That you can work out by taking a piece of paper and a cup of tea in the evening, right? So that you can easily calculate. You have to drink a lot of tea in the course. If you don't like tea, you can take green tea. If you don't like green tea, coffee is fine. But coffee, if you don't like, then hot chocolate. Okay, yeah, something that you enjoy, because you should enjoy mathematics, right? This is the beauty. Now there are some of the properties of entropies which I think again probably. Have you heard of concave function, convex function, right? This is, I'm just recalling. A function f is concave if f of x plus y by 2 is at least f of x plus f of y divided by 2. It's strictly concave if equality is not there, right? So which is fairly straightforward definition of a concave function. Jensen's inequality. This is a really beautiful inequality. So if f is continuous, strictly concave function on an interval I, and suppose ai's are positive numbers, such that their sum is 1, then summation of ai f of xi will be less than or equal to f of summation of ai xi I is equal to 1 to n. By the way, so you must have done a lot of work for for your JEE exam, right? Which book you followed for inequality? No book, huh? So George Polya has written a very nice book, which you look at, No, Hardy has written a very nice book, Inequality, which you can look at it. Anyway, so this is Jensen's inequality. And equality holds if and only if x1 is equal to x2 is equal to x3 is equal to xn. Example, log 2 base x is a strictly concave function on the interval 0 to infinity. Okay, so I think this is a very celebrated result. Can you prove it, by the way? So you again require some t to prove it, right? So Jensen's inequality, right? So we can actually use this inequality. So we have this result. Suppose x bar is a discrete random variable having a probability distribution that takes on the values p1, p2, pn, positive. Then entropy of x cannot exceed log 2 base n. Beautiful result. With equality if and only if pi is equal to 1 by n. It's a very important result. Entropy of a random variable x cannot exceed log 2 base n. So the questions that can be asked, for example, I love those kind of questions. Give an example of a random variable x such that entropy of x is strictly less than log 2 base n. Right? It's a type 2 problem. Give an example of a random variable x such that entropy of x is strictly less than log 2 base n. If you think about it, you will learn something new. Okay. Anyway, so this is a clear-cut example of Jensen's inequality. We know that h of x bar, entropy of x bar is this formula directly definition minus summation I is equal to 1 to n pi log 2 base pi, right? This can be written as okay. So this because of the negative sign, it goes to log 2 base 1 over pi. And this quantity, I can just apply the Jensen's inequality will be log 2 base summation I is equal to 1 to n pi times 1 over pi, which is 1, right? So 1 you sum n times, you get log 2 base n. Right? So this is something fairly straightforward. Okay, another result, entropy of x comma y cannot exceed entropy of x plus entropy of y for two discrete random variables x and y. Why do we need this? Actually, when we look at crypto systems, we are going to compute the entropies. Okay, so we need these formulas. And with equality, if and only if x and y are independent random variables. So suppose x is a random variable. So these values are x1, x2, x3, xm, and for y it is y1, y2, y3, yn. So pi is the probability that x takes on xi, and aj is probability that y is equal to yj. If rij is this number, probability that x, x is equal to xi and y is equal to yj, then pi I can compute is equal to summation of rij, right? I'm just substituting this value. And suppose qij is this quantity. Qj is summation of rij, I is equal to 1 to m. So once we have these things, then I can compute hxy. So I'm taking right hand side hx plus hy. Okay. So hx plus hy, I just compute the formulas, right? Pi log 2 base pi plus qj log 2 base qj, right? Then I substitute the values of pi and qj here. You get something like this. After simplification, it turns out to be double summation rij log 2 base pi qj. So then we consider this difference hxy minus hx minus hy. So the first term here is direct formula of hxy, right? Okay. Then since we have this, minus will become plus all those simplifications. You can compute this value is this, and then you apply, again the inequality. This turns out to be less than or equal to this quantity. This sum will be 1 because this is the sum of all probabilities. This is log 2 base 1, which is 0. So that means this whole quantity is less than or equal to 0. We got the inequality. Okay. So essentially, we get this inequality. Okay, so I think that's all. Okay, for equality, there exists constant C such that Pi Qj divided by Rij is equal to C, and then you substitute C is equal to 1 and so on, actually, you know. So, okay, finally, I should say that we should know entropy of a random variable, this definition you should remember. Then you should know how to compute probability of a random variable, right? You should know Jensen's inequality because you have to simplify this result, hxy less than or equal to hx plus hy. Yes, that's all. Right.